Hi, good morning, everyone. Am I audible? So let's get started. Okay. So today we are going to see the array data structure, but we will also have to study something on the analysis, right? So in order to understand array, so all of us know what is an array. So most of you have done computer programming and you have learned in the previous courses, etc. You have used arrays. So basically, when you want to store an individual number, like when you want to store, say, like age, or you want to store something like an individual data, name, etc., you can store it in a variable. But when you want to store a list of elements which are of the same type, I want to store all the marks of all students of this session, or I want to store the names of all students enrolled for this session, then I have to have a collection of data. And when you have a homogeneous collection of data item, the first easiest data structure that is used to represent is the array data structure. So arrays are always stored in continuous memory location. So depending on what is the size of the data we are storing, the address increments. But if you have the start address, you can easily compute all the addresses of the various index elements. So index variably starts from 0 or 1 based on how you write it in the program. But the first array, it is incremental. It is put into continuous memory location. Now, if I need to store for 50 number of students, I generally indicate the maximum size the array can hold. If I'm not aware of the maximum size, if I have some basic detail about how much max we can use it, so it's better always to indicate a maximum size. Otherwise, unnecessary unlimited of memory will be allotted. So we can you have that as a practice. And when a program works with many variables which holds comparable amounts of data, that is, you have the same type of data and you want to frequently compare them, use them for processing, you want to derive some insights out of them, then or difficulty comes in. I can just write, I can also have 50 variables. I can say int student one is equal to this, in student two is equal to this. I have to maintain the so many variables. Of course, the memory size will be same only, but to process them, it will be difficult. If you want to compare them, it will be difficult. So if you're not using arrays, the number of variables will increase. When I have the number of variables, of course, the memory size is going to be the same. But how do I process them? How do I retain them in the program? You cannot write simpler code, etc. So that is where array brings us the benefits. So when you use arrays, the number of variable reduces, so you can use a single name for multiple values and you can deal them with incremental indexes. That's the idea behind it, right? So how do you declare an array? You mentioned the data type. This is in C. So you declare the data type and then you mention the name of the array. This num is the name of the array. And you also mention the maximum size of the array. So this is array. So how do you read? Say I have an array of 4 numbers, right? Sorry. So how do you read the first number in an array? So if I want to find out what is this first number, how do I, what array notation will I use to read that number? How do I read that number in C language? Is any of you? I can give you mic access if you want to type or you want to yes, anyone? How do you read a number?
Then we
Yeah,
will
yes.
declare a variable and
Okay. So
in the
say
place
this is the array. Num. Name of the array is num. Okay, how do you read the first number?
then we can like declare the data type int and for first integer like first num equals to with num in brackets we have to use a first index number that is 0 ma'am.
Okay.
And that
Okay.
first number will be assigned to that variable and we can print that variable.
Okay, so num of 0 is what is the first variable, right? So num of 1 will be second. So let's say I have 9 here. I have 11, 20. Say I have 2 and I have 5. Okay. So to read 11, I have to say num of 1. To read 2, I have to say num of 2. So the index has to be represented. So 4 is when you declare 4 is the maximum length, but when you're reading it, the whatever is in the square bracket represents the index of the array, right? So if I have to read the entire array or I have to traverse through the entire array, what do? I start with the 0 index, the starting index, right? Then I run till less than 4. I don't equal to 4. So when I say less than 4, because we are starting, why do I say less than 4 here? Because I start from 0. So when I say num is maximum 4 means only 4 places will be there. Okay. So so that's why less than 4. So first time it will read what this will print. So enter the number. So you have an option to enter the number, right? And x will become x plus 1. Right? So basically, what will come in the screen when you run this? It will say enter the number 1 and you will enter something which will be added to this num of 0. The index is starting from 0. So num of 0 will be the first number. And when you say enter the number 2, you will enter the second number and num of 1 will store that second number. Say first time I enter 10, second time I enter 20, num of 1 will save in 20. And then again, this loop will run. X will be now 2 and it will ask enter the third number. So num of 2 will be 30. Right? So this is how the loop will run. Again, one more time it will run, asking you enter the fourth number, you will enter 40. So this will be the value of this. So if you want to ask for the input, this is how. And if I want to print it, how do I print it? If I want to print, say I have an array of n numbers stored in num of 4 and I want to print it. So the same loop I will do printf There will be no scanf. I'll just print the number is, and I have to just read the number, num of what? Num of 0. Then again, next time x will become 1, num of 1, num of 2. So num of the x I will write here. Instead of this, I have to just enter number percentage d, right? The num of x. Am I right or wrong? Is this clear with everyone?
Yes, ma'am.
Okay. Now there is some time complexity. Now there are some big O. This is called as big O. I will explain what is it. But when you look at this array, what all did we do? We read the array. That is, if the array is there, we read through what is in the array. We did an insert. So when you want to insert a number, you can insert. And when you want to delete an number, you can delete. And you can search for a number in the array or find the maximum element in an array, which we saw in the previous class. So all these are various operations you can perform on the array, right? So how much time each of the operations will take? What is the average case? What is the worst case? What is the even the best case? So this is something we have to understand. Then only we will know which when we want to compare. Say I have a array and I have a stack data structure. If I want to see which one is the best, should I use stack or should I use array? How do I compare it? So I have a piece of code like this, and in stack also I will have a piece of code like that. But I have to compare it means, like last time I told you, if you have to do an experimental measurement, you have to implement a stack, you have to implement an array, okay, and then say reading from the array is better, you have to measure the time, or reading from the stack is better, you have to measure the time and see which is less, and then say reading from the array is better, which is we saw the problems associated with experimental measurement in the previous session. So we cannot do experimental measurement always. So we need a method to calculate the time complexity without experimenting, without implementing the algorithm or the system, so that we know which algorithm is best. That is where asymptotic time complexity, asymptotic analysis comes in. Okay, so you have read has order of 1, insert has order of n, etc. Then you have this. So from this you can see that read is a simpler operation. Insert, delete, search are all equally takes an order of n times. So you know that this is easy, this is difficult, this takes less time, that takes more time by looking at the time complexity. But how do we calculate the time complexity? That is where we need to understand the asymptotic analysis, which I'm going to teach you now. Okay, so now are you clear that why do we need an analysis? Yes. Can we just go? So today I teach stack tomorrow, then I will start teaching queues, then I will go to linked list. But how do I compare these? How do I tell in array we did this? Same insert we can do in stack. Then what is the point of having a stack? What is the point of having a linked list? So there has to, I have to give you a valid reason, right? This data structure is suitable here. This data structure is not suitable here. This one performs well. So you need to understand the meaning. So comparing this, giving a real-time use case of this is better when you use this. So that is where the time complexity is useful. So that is why I am bringing in the time complexity example right away in the first session itself. Okay, so is this idea clear? So we have a basic understanding of array now. So with that, I'm going to go into the time complexity. Okay, so now before I go start with time complexity, I hope all of you have access to the eLearn page by now. Have you all got the access?
Yes, ma'am. You have got.
Yes. So I have uploaded the course handout as well as the week 1 PPT there. And there is also good um, recorded lectures available for every week. As I told you in the previous session, is just the minutes, not even 30 minutes. Sometimes it's even less than that. So small videos are there, which gives you refreshes you the concepts, gives you understanding of it. So please go and look at them. Okay, it will help you to understand the concept very well. So please be take some time out, 15-20 minutes per week to go through the videos and learn from it. So maximum 30 to 40 minutes is what you will need to go through the videos. Okay, fine. So now what is an algorithm? We looked at this in the previous session also, right? So what does algorithm, I think I'm sharing the wrong slide. So algorithm, as I mentioned, is a set of sequence of step-by-step instruction in which the system will perform the activities. It can be written in plain English using a pseudocode or using a flow chart, etc. And we saw an example of a pseudocode in the previous. So every algorithm will have an input and output, right? And three important things it should be clear and well defined. It should have a finite number of steps, and every step of the algorithm must lead us to the correct output. It should generate the correct output for us. So now, why do we need performance of an algorithm? This is again repetition of what we discussed in the previous session, right? So an algorithm will, how do we know whether an algorithm is good or bad, or it is better than the other, whether it is working? You have to analyze it. First of all, we should know whether it is giving the right output, whether it is working according to what is described in the problem statement. Does it have useful information? Is it in codable form? Can it be easily implemented, or it is an algorithm which cannot be implemented? Does it take less time to execute? Does it occupy less space, or it consumes more memory, etc.? So all these are ways in which we categorize the uh, structure analysis of whether the algorithm is good or bad. But specifically, this 5 and 6 is more on the performance of the algorithm. So performance is identified by time and space. So always we want an algorithm which performs in lesser time and lesser space. Even in practical life, we really want that, right? So what do we want in practical life? We want something which is uh, say very, we want good products, quality product, but with less cost, right? We want to go out, enjoy. We want to have high good experience, but don't want to spend much. We should don't want have more traffic. So all the same thing, like less time, less space. That is always the requirement, and we analyze a performance of an algorithm by time and space complexity. So this I explained in the last class. What is a problem with the experimental study? You write the algorithm, you implement it in the program, you run the program with the input size, then you use measurements like current milliseconds to measure the accurate time. Implementation is a must, and execution is highly biased based on the current input instance based on which you have run. And if you need to compare two algorithms, you should use the same environment, but mostly the same environment is hard to replicate. So your system and my system might be difficult. Hardware, software requirements might be difficult, or the number of programs I'm running on my system might be difficult. So there are various activities which kind of makes it difficult to compare these two algorithms by experimental studies. So that is why we need a analytical model, right? So you cannot practically implement everything before testing it or before analyzing it. So we need something simple without dependency on the hardware, software, without dependency on the input instance. We want a method to analyze the algorithm using a general methodology. It should use only the high level description of the algorithm. It should take into account all possible inputs, not just one input instance like we measure time here. It should take into account all possible inputs, and it should help us to evaluate the efficiency of an algorithm, which is independent of the hardware and software. So these three things has to be there in this analytical model to analyze an algorithm. Then only we can say it's a fair analysis and we can rely on it to judge between two algorithms which is better or not better. So such an analytical model is the asymptotic analysis of an algorithm, for which we assume that we have a random access mission. So random access mission, I told you in the last class, it is not memory. It's RAM is different. Random access mission is different. So we assume we have a hypothetical mission. Okay. This mission is a simple model of how computers work. It has a 32-bit CPU which supports sequential execution. What do I mean by sequential execution? How do what is a CPU? Central processing unit. So that is where all the processing starts, right? How is so that in that mission, you have a sequential execution. One step by step it executes. It doesn't jump steps or it doesn't do random execution. It goes in a sequence. And the memory capacity of a system, the memory cells holds the numbers, right? It can hold an arbitrary number of characters, etc. So memory cells are numbered and accessing any cell in the memory will take 1 unit of time. So if I want to read array, so say I have num of 0, I want to read num of 0 from the memory, it will take me 1 unit of time in the random access mission. So 1 unit of time for assignment and return 1 unit of time for arithmetic and logic operation. That is what is the RAM model takes. So using this RAM model, we measure the runtime of an algorithm by counting the number of steps it takes on a given problem instance. Okay, so we assume that primitive operations, primitive take 1 unit of time. If it's a loop or a complex operation, it takes much more amount of time. So we calculate that how much number of steps it takes on a given problem. And by assuming that if an algorithm executes or a RAM executes a given number of steps per second, the operation count converts easily to the actual runtime. So we are going to give our result in representation of n. What is n? N is the input size. So this entire asymptotic analysis or this way, the analytical model we are using to analyze the algorithm, we are going to represent the runtime not in seconds, not in microseconds, but in terms of the input size. Okay. So here, when I run this, say I implement an algorithm and I get the current time in milliseconds and I subtract it, I will get something like 2 seconds, 1 second, or even 1 microsecond like that, right? So this is, I'm measuring it, the difference of time in milliseconds or seconds. But here in this analytical model, I'm not going to go with seconds, microseconds, or etc. because it is independent of the hardware and software, and it should take into account all possible inputs. So that is why we are taking input size as the measure. So the RAM model will, for each step, how many times it will execute for that given n input of size. That is how it calculates. And RAM executes a given number of steps per second. So the operation count will be actual runtime of the algorithm for the given input size. Yeah. Okay. So now is it clear that what is the difference between an analytical model and an experimental model? Yes. So
Yes,
what
ma'am.
are we doing differently? We are not going to calculate the real time. We are coming up with a model which we will be able to calculate. So how I'm going to do that is what? So primitive operation, basic computations, uh, identifiable in the pseudocode. It is not independent from the programming language. Exact definition is not important, right? So primitive operations like assigning a value, calling a method, perform an arithmetic operation, comparing two numbers, indexing into an array, following an object reference, all this comes under returning from a method. All these are simple primitive operations. So all these primitive operations take exactly 1 unit of time. Simple operations, arithmetic operations, reading, all these are simple operations which take just 1 unit of time. So constant time. Okay, when I say one time step, it's a constant time. So 5 seconds, 1 second like that. But we are not saying seconds here, but we are saying 1 unit of time. Loops and subroutines are not simple primitive operations. They have to be repeated. And all the steps inside the loop and subroutines, they are have to be repeated again based on the number of times the loop will run. So loops are nothing but a composition of many single steps which gets repeated again and again. So the time taken to run a loop or execute a subprogram depends on number of times the loop will iterate. So the number of loop iterations is what will determine the total time the loop will take. So it is not a constant. So the number of loop iterations will depend on what? How many times a loop will run will depend mostly on in an array what it so you access through the array, right? For loop you write, right? So how many times did the for loop run in our example array? When we saw array example num
N
of
minus
4,
one times.
n minus 1 time. So if we have 4 elements, it will run 4 times, right? I mean starting time, and it will run 4 times, or it depends on the input size, depending on the program. So the number of loop iterations is dependent on the input size, right? So the number of loop iterations is dependent on the input size, and the number of times the loop, the time taken to run a loop will depend on the number of iterations it is running. And each memory access also will take 1 unit of time because it is also a primitive operation, and the RAM model takes no notice of whether the item is in cache or disk, etc. So we assume this RAM model has infinite amount of memory. So everything is in this memory and it gives us the same time. So every memory access will be 1 unit of time only, whether it is in the cache or it is in the disk or it is in the secondary memory. So based on this, we are going to calculate the running time. So this is what we saw in the last class. Okay, so now I'm going to repeat this, but a small difference I'm going to make. Explicitly, we had done a few mistakes here. So now, when you say pseudocode, right, we can determine what is pseudocode, first of all. It should be independent of the hardware and software environment, right? So this particular part here, if I'm written like I'm writing it in a software C program, right? But actually in a pseudocode, how do you write this? So this is how you actually write it. Okay. Okay, there is a reason why we are doing this. Okay, to tell you the difference also and to tell you something else. Okay. Now tell me, we will calculate the time. Okay. Let me copy this. Let me open a whiteboard. Okay, I copied this. So we will start calculating the time. So how much time this first line will take? Current max of A of 0 value. A is the array. N is the maximum input size. Are you able to see see this one? The whiteboard is visible to all of you, right?
Yes, ma'am.
Yes.
Okay. Okay, fine. Good. So this first line, how much time it will take? What are the operations which is happening here? We are
Getting a value
yes,
and inserting into
yeah.
current maximum.
Yes,
Two
we are
operations.
reading the value from A of 0, that is the first index of the array, and we are assigning it to a variable. So two operations, one is accessing memory, second is assigning to a variable. So we are writing two here. Okay. In this step, what is happening? The loop starts. So for the loop to start, you have I is equal to 1, which is an assignment. Right? When the loop starts. So this I is assigned 1. So that is taking 1 unit of time, right? And how much time, how many times the loop will run? How many times this loop will run?
N minus 1 time.
N minus 1 times, right? So, but you have N here. I will tell you the reason why you have N. The nth time, right? So first time I will be 1. It will go inside the loop, perform this. Second time when it comes, I will be 2, 3, 4, like that. The nth time, again, it will come here and again check whether I is less than n. Okay, it has to run I is equal to 1 to n. So every time when it performs I becomes 2, it will again come and compare whether I is less than n or greater than n. If it's less than n, it will go inside the loop. If it is greater than n, it will come out outside. So this comparison, right? It happens for the nth time also, but nth time that comparison will be false. So the loop, the statements inside the loop will not get executed and it will return here. But this statement, this comparison also, how many times does it happen? N times. Do you get it?
Yes, ma'am.
So this assignment happens only once in the for loop. The loop runs n minus 1 times. That is exactly correct. 1, 2 less than n. But this comparison I less than n happens n times. Okay. So that is why they have taken 1 plus 2n here. Or you can also take it as 1 plus n Okay, leaving this 2 here because this increment, right? This increment is depends on the programming language. And it runs n minus 1 times only, right? So I is a index. It is incremented. So you need not treat this as a assignment or arithmetic operation. So that is why I told you you can write it. This way of writing gives you a little wronger picture because this is the for syntax for C programming language. But in pseudocode, we write it like this: for I is equal to 1 to n. So first assignment I is equal to 1 happens. Then in the next assignment and all, I is compared with the n, and that happens n times. If you want that every time the assignment also happens, like I is equal to I plus 1 also, if you want to assign I plus plus, which is happening, that also if you want to give time, then you can still have 2 here, though it will happen only n minus 1 time. So basically it is 1 plus 2n plus n minus 1 time. That is how it is. Okay, so n minus 1 times only this I plus plus will happen. This part. Okay, so that is why we say this is 2n. But all these are very significant smaller activities, so it doesn't matter. So why I'm repeating this again here is you might have your book explained, taken into account this part. In the video, they might have taken into account this part. So that is why I'm giving you both the flavors in the class so that you should not have this doubt in the future. Okay. But this factor, whether it is 2n or 3n, so what will happen? It will become this 1 and 1 will cancel. So this becomes 3n. Instead of 2n, it will be 3n. Okay. So that way also you can take into account. But this is a very, here if you take only assignment and the loop increment, then it will be just 1 plus 2n or just 2n. Okay. So you can leave out this 2 also. So let's keep it 1 plus 2n for our understanding itself. Now, how many times these steps inside the loop will run? N minus 1 times. Right? Okay. So this n minus 1 times, what happens if this particular step, right? This is an array, reading from an array and comparing with the current max. So two points are here, right? And this 2 points, how many times it runs? N minus 1 times. 1 time for every loop iteration. So it runs n minus 1 times. So that's why it's 2 into n minus 1. And then again, this is an assignment operation. So if this assignment operation, let me explain with an example. I'll clear all this. I'll bring the slide again. So let me add a text. Okay, let me add a array. I say I have 4 numbers: 9, 4, 5. Okay, these. Okay, are you able to see this number?
Yes, ma'am.
So let's say uh, this is my array A. Okay, and this is A of 0, A of 1, A of 2, and A of 3. Okay, say this is my array. Now let's run this example. Okay, now what will be the first current max value? current max, what will be current max first time? You can type in chat or 9, right? So
Yes,
this will be
ma'am.
9. 9. So now I will be 1, right? And A of I greater than current max. So what will be A of I? 4
4.
greater than 9. So this statement is false. So this statement will not execute. Okay. First time. When I becomes 2, what will happen?
Current max will be 5, ma'am.
So when I becomes 2, it will be 5. 5 greater than 9. So again, the statement will not execute. Then I is equal to 3. Again, what will be the statement? 3 greater than 9. Again, the statement will not execute. So if you look for this particular example, this statement execution is 0. Correct? None of the time this particular current max assignment worked at all. Okay, let me change the let me change this. Okay, so let's say we will change the array. All of you understand why current max A of I is not getting executed, no? So let's say I go with a different array now. Let's say I put, I have 9, then I will have 3, then I will have 11, then I will have, so sorry. Okay, so say I have this. Eleven, 9, 11, 5, 7. Okay. So now how many times this current max will execute? First time A of current max will be 9. So when A of I is 1, then it will say 11 greater than 9, which is true. So current max will run 1 time. So current max will become 11. Correct? So this statement will execute once. In the second iteration, again, when I is equal to 2, then again 5 will be compared with 11. 5 greater than 11. This is false. So this statement will not execute. In the third step, 7 will be compared with 11. It's false. So this statement again will not execute. So only one time this executed. Okay. So in best case, it will have run 0 times because first itself you will identify the max number. In some of the cases, it might run 1 times. What will be the worst case? How many times this will run on the worst case? Any idea? When you will get a worst case? Let me add a number. 2, 4, 5. So this is my number. Okay, 2, 4, 5, 9. So what will be the current max first time?
2.
The current max will be 2, right? So first time it will compare 4 greater than 2. So correct. So current max will run one time. Second time it will compare 5. So this will become 4. Right? This will execute and this will become 4. Now again 5 greater than 4 it will compare, which is also true. So this will become again 5 and this again it is running. Then in the third time, it will again compare 9 greater than 5. Right? Again, this will run and this will become 9. So when you have such a kind of a input, when the maximum number is in the last position, you get the worst case. When the maximum number is in the first position, you get the best case. It runs 0 times. When in this case, you saw current max runs only 0 times. This statement, I'm saying this particular statement runs 0 times. In this case, it runs how many times? Here it runs 3 times, but it is n minus 1 times. So worst case, it will run n minus 1 time. Best case, it will run 0 time. On an average case, it might run anywhere in between, right? Depending on the instance. So it is better always to give the worst case time complexity. Why do we give worst case time complexity? Is we are telling that maximum time it will take to run is this, but it will take lesser time than that also. So it is when you say I will complete this activity in one day, I expect you to give me the result within 24 hours, right? If you say I will submit only after 48 hours, then you should not say I will do in one day. You should say I will do in 2 days. Right. So always we have to look at the upper limit, the maximum time, the worst case it will take to execute that algorithm. So that is why we put 2 into n minus 1. 1 is for reading from the memory, 1 is for assignment. And how many times it will run? Maximum on the worst scenario, it will run n minus 1. If it's best, it will run 0. If it is in between, it will run, but it will not go above n minus 1. So that is why we put 2 into n minus 1. And this return max is what? Only 1. Okay. So now if you add all this, right? If you add all this, I'll stop sharing the whiteboard. Right? What you will get? Two n, 8n, this 1 plus 2, 3, minus 3. Minus 6. So minus 3. Okay. So depending on whether this is used in the algorithm and in the recording and in the book, you might see a difference here. So I think there it will be 7n minus 2. Okay, but both are correct. So there what they have done is they have not taken into account this one. Okay, they have just mentioned it as 2n only. Okay, so that is what is the problem, but it's okay. But say I get 7n minus 2 or 8n minus 3, the asymptotic complexity is going to be the same. I will explain that why. Okay, now we will get into asymptotic notation. Now, before I get into asymptotic notation, how many of you are clear in how I calculated this time per step? Or how many of you still have doubt? Shall I give you one basic example for you to add? Tell me. Shall we do one basic example to test if your understanding is right, and then we proceed to asymptotic analysis?
Okay, ma'am.
Okay, fine. So I will give you one small for loop, one small algorithm. It doesn't have any meaning. I'm just giving you something, okay? Say I take a variable temp and I assign it a variable a of 0. Then I have a for loop which runs I is equal to 1 to n. And inside the for loop, I say a of a equal to n plus 1. And once the for loop is over, I return in return the entire array. Okay. So this is a simple one. So tell me, you have to tell me the number. You don't have to tell me the entire one. You have to just tell me one, the time for each of these steps. Okay. Let's take a break also now. So I will leave this open. You have to calculate this. When I come back, we'll take a 10 minutes break. When I come back, you have to tell me the time taken by each of these steps in terms of n. Okay. Okay, so have you completed it? So can you tell me what is the first one? What is the time taken for first one?
Row of one, ma'am.
Sorry,
One.
one.
Constant.
You can type in the chat. Your voice is not clear. One or two?
It's 2.
It's two, right? One for the assignment, one for the reading from the memory. So it's two. Okay. So it is two. What about this statement? How many times the loop runs? In this
N
case,
times.
n times. Why n? It starts from 1, 2, 3, n. Nth time it will not go inside, or if it's in if the input is not there, but still checking will happen, right? So it is the loop runs n times from I is equal to 1. I say n is let's say n is equal to 4. Okay, so first time I is equal to 1. Second time I will be 2. Then third time I will be 3. Fourth time I will be 4. So 4 times the loop will run. Right? Based on the condition, whether I less than n or not, then it will maybe reduce one time. But here, according to this, we have not given any details, so it will run n times. Right? Okay. What about this step?
2 plus n minus 1.
So individually, it will take one addition plus one assignment, right? So it is 2. How many times the loop will run?
N minus 1 time.
By n minus 1.
Because like nth time it won't come to loop, right, ma'am? It will terminate
Yeah.
it upper side.
Okay. So you are following the logic of the current max. Okay, I have not explicitly mentioned it anywhere. But if I have mentioned it I less than equal to n, or if I mention I less than n, then only you can clearly decide whether it is n or n minus 1. Correct?
Yes, ma'am.
Okay, so let's say I have given, I have not declared it. So if I have not declared it, or if it's not clear, what will you do? What should you do? You should take always the worst case, right?
Yes, ma'am.
So we'll take n
Yes,
here.
yes, ma'am.
Okay.
Yes,
So
ma'am.
whenever you are not sure whether it will run n minus 1 time or n time, you don't have the information, or you always go for the maximum, the worst case complexity. So if loop also, we're not sure, because for this instance, it might run 2 times, but for the other instances, it might not run 2 times. So that is where you have to go for n here. But this pseudo code represents I is equal to 1 to n, means I will have 4 iterations, n iterations. That is what it means. Okay, if it's going to run n minus 1 time, then they have to give it like this. That is the pseudo code notation. Okay, so you have to consider this as n only. Okay, there they have given explicitly this, and so we know that it will run only till I less than, in terms of the current max, they have mentioned I less than n. So you know it runs only n minus 1 time, but here they have not mentioned anything, so which means the loop will run n times only. So you don't have to make it n minus 1. And what about this return a statement? How much time it will take? It's a simple return statement. So one
One.
time.
One time.
Okay. Because it is an array, do I have to say n here? Or is it one is enough? It is a return statement only, right? Simple return. So should I say it is one or n? It can be one only. There are two reasons. All return statements, it's simple. It just returns the address of the memory location only. So it is one only. And moreover, in an array, we just always return the first index element only. Then incrementally, because they are in continuous homogeneous location, continuous memory location, we can calculate other indexes easily from the starting point. So generally, we don't send any individual arrays if they don't need it. So we are returning the entire array. One is sufficient. So if you add all this, what do you get? Tn plus 3,
3 plus 3n.
right? This is what is the function we get. So this is called as f of n. F of n is equal to 3n plus 3. This is the asymptotic function, or this is f of n, which is a function. We are representing the running time of an algorithm using a function. So n is the input size. So this is called as f of n. For algorithm current max, f of n is equal to 8n minus 3 or 7n, depending on the implementation, it's 7n minus 2. But this is the f of n. Okay. Now, let's go to algorithmic complexity. So we have the f of n representations like this. Now, what is asymptotic notation? It is a way of classifying them. Okay. So I have a function f of n is equal to 7n minus 3. I have a algorithm which has f of n as 7n plus 2. 3n plus 3. But what does it mean? Whether this algorithm is better or that algorithm is better? How do I know? Right? So that is where asymptotic notation comes as a way to speak about the functions and classify them. Okay. So we have big O notation. Then we have, so first we will see big O. Okay, then we will come into the theta notation and the gamma notation, etc. So when you say big O, what we are doing is we are trying to get a upper bound. Okay, we are trying to get a upper bound value for a function, telling that this function or this algorithm will not go beyond this upper bound. The running time of that algorithm will not go beyond that running time. Okay, so upper bound. So big O notation is basically to represent an upper bound. So telling that this will not go above this particular factor. So our f of n is this. Okay, say we had f of n equal to this, right? What was our f of n? 3n plus 3, 8. So let's write f of n. Let's take our f of n as 3n plus 3. Okay. Now, so this is our n. Let's say we have one c into g of n. So G of n. Let's say we have C is equal to some 10. And n naught is equal to 5. So what we have to see is for all the values of n greater than n naught, that is above 5. Okay, above 5, n1, n2, all these values for any value greater than n naught. Okay, n can be any number, any positive number greater than n naught. The C of Gn, if you plot it, right? The C of G of n function, if you plot it, it should always be, the f of n value should always be lesser than it. That is the idea. Okay. So if it's lesser, if it is, say, this is the maximum upper bound. So I should not have a graph where after n naught, say this is my n naught, after n naught, my f of n goes above C of G of n. After n naught, always f of n should be below, that is less than C of G of n. So that is what represented by big O notation. Okay. So we have to represent a function or represent a value, tell that value that above this, it is always the C of, this is the upper bound of this algorithm. The algorithm f of n will never be less than, sorry, will never be greater than this particular big O of n. So that is what we say when we say a big O notation. Okay. So when we say big O of G of n, so this f of n will be always less than C of G of n. So let's take one example. So when we say f of n is equal to 3n plus 3, okay, we will ignore the constants and we'll say this function is of big O of n. And when we say f of n is equal to 5n squared plus 3, we will again ignore this constant and say this function is of order big O of n squared. Okay. So similarly, you can say order of n. So 2n squared plus 10n. So you will ignore this. Take the biggest. You will delete or you will ignore the smaller terms and you will take the higher term and ignore the constant. So order of n squared. So always in big O notation, you ignore the lower terms and you take the highest term and ignore the constant. That is how you will calculate. So this is, so again for this also you will ignore the lower terms, ignore the constant and take the n squared. Okay. So now one question might come to you. So tell me what is the big O notation for 10n plus 25? What is the big O notation for 10n plus 25? What is the highest term here? My f of n is 10n plus 25. Okay. So what is the highest term here? Twenty-five is highest term or 10n is the highest term?
I'm 25.
No, 10n plus 25. So this is a constant, right? 10 yen. It depends on the value of yen, but you cannot say which will be the highest term, constant or 10 yen. So in this, which is the highest term? 125 n squared is the highest term, right?
Yes, ma'am.
So similarly, in this, which is the highest term? For any value of yen. Don't take the literal value. For any value of yen, which will be the highest term? 25 value will not change with respect to yen. But for n is equal to 100, we will have a different value. N is equal to 1, we will have a different value. So that is why we have a lower bound of yen naught. So this is the highest term here, 10 yen, for any value of yen, right? For a higher value of yen. So we take the yen, the highest term, we ignore the constant and we say this is big O of yen. Okay, so this algorithm runs in the time complexity of n. This algorithm runs in time complexity of n squared. So that's how we say when we write a big O notation. Okay, so it might be a little confusing today to you at this point of time, but when you look at examples, right, when you actually compare it with the algorithm, you will understand it better. Okay, now if I have a let me show you one example. Just give me a second. I have to pull out a sheet. Okay, all of you go back to the whiteboard. Okay. So I have taken example from the video and the book. Okay, so now consider the function is the whiteboard visible? Yes or no?
Yes,
ma'am.
yes, yes.
Okay, fine. So you can see the asymptotic notation slide, right? You're able to see the slide? Example 1, asymptotic notation in the whiteboard.
Yes, ma'am.
Okay, fine. So you have a function f of n is equal to 2n plus 10. Okay, so this blue line here represents that notation, and we are mapping that line in a graph from n is equal to 1 to n is equal to 1000. Okay, you are having that line. Now, f of n can be big O of g of n if there exist constants c and n naught such that f of n is always less than c into g of n for any greater value of n. Let's take an example. Okay, f of n is, let's say it's big O of n. We are taking, so how do we always calculate big O is we ignore the lower order terms, we select the highest term and then we ignore the constant. So same way I did, I ignored the constant, then it's big O of n. Okay, so let's take some random number. C is equal to 3 and n is equal to, n naught is equal to 10. Okay, and if I plot this in the graph 2n plus 10, right? This is the n, right? This 3n. So if I make it 3n, okay? 3n plus 10, right? So if you look at this graph, the dotted line, which is representing 3n, which is g of n, it is always greater. So after this n is this point, right? You can see this c, this is c of g of n. Okay, the blue line is our function f of n. F of n is always lesser and c of g of n is always greater. So does this hold true? Okay, so the upper bound for this function f of n, which is for an algorithm, is big O of n. So it will not run above it. The big O of n, it will not run above it for any value greater than n naught. Okay, so the n naught is 10 here. So this will not run any for any value greater than n naught. Okay, so usually I will tell you a small trick that how do you actually calculate g of n generally is what we do is whenever we have a f of n, what we generally do is we take all these terms as n. Okay, so 2n plus n, and then we give the maximum en. Okay, so say if I have f of n is equal to 5n squared plus 6n plus 10 means I will take all of them. I will add the constants 5 plus 6 plus 10, which is 21. Okay, and I will write n squared, 21 n squared. This is what is g of n. Okay, usually we will write. So if I say have 5n plus 2, okay, is f of n. Okay, we will usually take g of n to be what? 7n. How I get 7n? This is a small calculation just to ensure that it is always lesser the upper bound. But the asymptotic, we get always take the higher order term. How to calculate big O of n? Always take the higher order value, ignore the constant. Okay, that is what is the asymptotic notation. Now, why this is useful? Why do you think this is useful? Why do you think this will be useful? Any idea, anyone? Why do we need an upper bound? Any idea why do we need upper bound? What do we do with upper bound? Okay, let me give you a very practical example. You want to go on a trip, okay? And you want to plan your expenses for the trip, right? How do you decide which is the how much money you need? You will go to your friend who has already gone to that place or on the trip, right? And you will say, you will ask him, right? What is the maximum amount he has spent in that? Will you ask minimum amount or maximum amount? When you ask your friend to ask if you want to plan your trip or expenses, and you want to go, your friend has already gone some time back, and you want to plan your trip for the next week, coming week. So how much money he spent, or how much was the travel expenses, or how much was the boarding expenses? What is the minimum boarding expenses or maximum boarding expenses?
Mm, maximum, ma'am.
Why do you ask maximum?
We get to know the idea of how much we maximum going to spend on the trip.
Yes. So when you want to plan your resources, right? When you how much money you have to take, how much money you have to have in your wallet, that depends on the maximum we would need. So upper bound. So we have to plan our resources. So when you know the upper bound time complexity, you can plan your resources. So if you compare, right? You can so when you want to compare two algorithms, we always compare with the worst case time complexity, the maximum one. So that is why upper bound is more useful. Okay, the big O notation is more useful because you always calculate time complexity based on the upper bound, because that gives the maximum time, the worst case complexity. Okay, so now let's look at another example, same, to give you more clarity. Now we are having a function f of n squared. The function is f of n squared. Now this is not order of n. Okay, it has to be order of n squared. We go of n squared, but it is not order of n. I want to explain why it is not order of n. Okay, so this is blue line is n squared. You can see. Okay, and for any value greater than n naught, you can see this at 10n, it is at this point. After this point, you can see f of n exceeds. For 100 n also, you can see after this point, it exceeds. So g of n cannot be n in terms of n. Okay, so this is not order of n squared. Okay, so what is the order for this? It is order of n squared. So if you draw n squared graph, it will always be, sorry. If you draw an n squared graph for any value of greater than c, you will see that after some, if you start here also, for after some point, it will always be greater than f of n after this particular point. But this line, it becomes less after certain point, it becomes less after. So it is order of n squared. Okay. So now my question is, you are telling a upper bound, right? You are saying f, now tell me what is the answer. So I have a f of n is equal to 7n minus 2. So tell me what is the big O for this function? What is g of n? 7n minus 2. How will you calculate the time complexity for this? I just told you, no, ignore the constants, take the higher order term. So what will be 7n minus 2? Yes, anyone? So which is the highest term here?
7n.
7n, right? So you will ignore the constant. So this is order of n.
Okay.
So this is the upper bound. How do you calculate g of n? I'm telling you how do you calculate g of n? You add the constants 7 plus 2 or 7 minus 2, whatever. 7 plus 2, you add the constants 9 and put it in the higher order term n. So g of n is 9n. So the big O is order of n. Now this I'm saying order of n is upper term, the upper bound, right? Now, what if I say this is n squared? Order of n is upper bound. This is also true, right? If order of n is itself great, order of n squared is also greater only, right? So can order of n squared be the upper bound for f of n? Yes or no? So when here it's like I'm saying 5 is less than 50. When I say this, here it's like I'm saying 5 is less than 500. If this is true, this is also true only, right? But why I'm not giving the upper bound as order of n squared? Okay, don't worry about why. Is it this right? Can I say upper bound of order of n squared for this f of n is equal to 7n minus 2? Yes or no? Logically, is it correct or not?
Ma'am, can you repeat once more?
Okay. I'm saying the upper bound time complexity of this function f of n equal to 7n minus 2 is order of n. It is also order of n squared. I'm saying it can be order of n squared also, the upper bound value. I'm saying this f of n value for any value greater than c and n naught, this f of n value will not exceed order of n. It will also not exceed order of n squared. Is it true or not logically?
Yes, ma'am. It will not exceed it.
It will not exceed, right? So order of n squared is right. Even order of n cube is also right. Right? It's like I'm saying 5 is less than 50, 5 is less than 500, 5 is less than 5,000. Everything is right only. But
Yes.
why I'm selecting this as the big O of n, not n squared and n3 is I have to give the best approximation. This is an approximation I'm making, right? This is an approximation. I'm telling this algorithm will run in order of n times, right? I can say this algorithm will run in order of n squared time. The upper bound is n squared. So if you want to reach a place from your home to office and you are new to the place, when you ask your friend, he will say he should give you the maximum time it will take to reach that place, right? Say if it takes 20 minutes, he can say one day it took him 20 minutes. Okay, and one day it took him 25 minutes, and another day it took him like say 18 minutes, he should say 30 minutes is the maximum time it will take you to reach the office. But he can also say 2 hours is the maximum time which will take you to reach the office. That is also by logic, it is the correct statement. But what will you expect from your friend? The nearest approximation possible, right? So the same way, when you say the upper bound, we can still say the upper bound can be order of n3, n squared, n also, but the nearest approximation is what we want to say. So that is why we take this method, take the highest term, ignore the constants and give the big O notation. Okay, you understood why we are taking the biggest term and adding the constant, etc.
Yes,
Understood?
ma'am. Yes.
Okay, clear. So now let me go back to the PPT. Some of you might feel this is very difficult at this point of time. It looks a little complex because you don't have to apply this directly right now. You have not applied this, or it looks like jargons. Why are we doing this? But when you compare, when you start doing in the next class, when we start simple operations in arrays, and when we say this is the time complexity, it will make a lot of sense to you as and when we compare it. Okay. So don't worry if you're not getting the full concept also. If you're able to understand the lines I'm saying, it is enough. So now as we say big O is the upper bound, we also have a lower bound concept, which is the big omega. So here we are saying that the minimum time, right? So the same concept here, we have a C of G of n for n greater than n naught. F of n will not go beyond less than this. So the minimum lower bound is what we are representing by big omega. Okay. So how do we calculate big omega is, same concept, say f of n is equal to 5n plus. There we added, for big omega, we added 7 and then we said 7n. So here we will just remove, not add anything, take the highest term alone. So 5n is what we will say as the lower bound. Okay, and big O of n will be the time complexity. So that's the lower bound. Now there is now something called as theta also, which is tight bound. We had upper bound, we had lower bound, then we have something called as tight bound. Tight bound gives both the upper and the lower bound. So the f of n value will always lie between these two functions, c1 of g of n and c2 of g of n. That is what we will say in big theta. Okay, so I will explain big theta a little more in detail, and when you do examples, we will get more clarity. So I'm not going into go into that at this point of time. Okay, now we will go back to our array example. Okay, so what did we do in the array example? We just looked at how to traverse it, right? So we will look at something more on what can we do there. Okay. Just sharing the slide again. Is it visible? My audio is clear, right? Because it's raining here. I think the power is also shut down. So I'm not sure how much time I will run. Let me see. Okay, if I get disconnected in between, then you can log off. We will meet in the next session. Okay, let me continue. So now we have these operations, read, insert, delete, search. And now does it make a little sense to you that we are saying that this read operation takes order of one time means I'm just reading. So it's a constant time. There is no input involved at all. I'm just reading one variable means it just takes one order of one time. The average case and the worst case is order of n. Insert takes order of n. Why do you think insert takes order of n time in an array? How do you insert into an array? First of all, we should know how to insert into an array, right? How do you insert into array? So let's say I have an array 5, 6, 7, 8. So if I want to insert into an array, I have to insert at the end or in between also. What I have to do? I have to go traverse, right? I have to reach the end of the array. So I have to say I is equal to I plus 1. I have to go a of 0, a of 1, a of 2, a of 3. Then reach the end and then add one more element. So that is why it takes order of n. We will see algorithmically in detail in the next session. Delete also, if I want to delete an element, how do I delete in an array? First of all, I have to search through the array, right? I have to find the element and then delete it, right? So if I want to delete a single element, I have to traverse through the entire array. So what is the worst case time for traversing through an array? How many times this loop will run? If array is of size 4, how many times this loop will run? Array is size 4, how many times this loop will run?
4 times, ma'am.
4 times. So the traversing of the array depends on n times. And for delete, search, and insert, I have to traverse through the entire array. So it depends on input size of the array. So that is why we have order of n everywhere here. Okay, so insert operation might be something like f of n is equal to 5n minus 2 or 3n plus 3, something like that. So all these are functions of n. So that is why the time complexity is also in terms of order of n. Okay. Okay, let me give you a small activity. Say we have an integer array with 10 elements. Okay. And in that 10 elements, I want to see if 22 as a number is available. Say A maximum size is 10. Okay. And I want to see if 22 is available in the array. What is the logic I will use to do this? How will I find if 22 is in the array? How will you find 22 is present in the array or not? What kind of logic will you go ahead with? You would have done some programming like this example, right? So tell me in programming steps, you would have learned C programming, right? So how do you go through the arrays? How will you find 22 inside the array?
And by using for loop, iterating through the array, finding, and in for loop, if in if statement, if in array a equals to that number, and we'll return that I
Okay.
index.
So probably what you will do, you're saying that you will run from I is equal to 1 to say n minus n. Okay. First index to last index you will run and you will compare that array value if it's equal to 22. What will you do if it's 22?
Return that index.
Retain that index. Okay, you save that in a temporary variable like something. Okay, then will you stop execution or you will continue till n minus 1? Till n.
Uh, we can stop there, right?
Okay. Okay, you can stop. So if you, I just asked you to find one instance of 22, you can stop. So in I will be the number of times the loop executed because you're starting from 1. If you find, if the 22 number is first present in the first place itself, right? One time in one iteration only you will find out. But if the I is present in the last place, then you have to do a linear search. You have to search through the entire array, right? So that is the problem. So to find one number, say the array size is 100. Okay, and you to find one number, you have to search through the entire array. So 100 n, yeah, that will be the time complexity. Can we reduce this by half? What are the options? That is where the concept of binary search comes in. So you understood what you are doing is a linear search. When we are linear search, we search in index 0, we search in index 1, we search in index 2, 3, 4, 5, we go one by one and search. If the element we are searching is present at the end, then it takes we have to traverse through the entire array and the worst case time complexity is order of n. And for larger numbers, this is like wasting a lot of time. So how do we improve it? How do we simplify it? So we take very less time. So that is where we bring in the binary search concept. Okay. So binary search, I will start in the next class because we have to do some practical examples of this also. So we will continue in the next class. I'm stopping here today a little early because there is no power and it's raining heavily here. So we will continue in the next session. Thank you. I'll just stop the recording. Any of you have any questions?
No, ma'am. All good.
Okay. Okay, fine. We'll meet in the next session. Bye.
Okay, ma'am. Thank you.